Okay, so our goal here is to talk about different kinds of probability, specifically dependent and independent probability. But in order to do that, we got to first start by talking about outcomes. Outcomes are the possible results of an action. So if you're flipping a coin, there are only two outcomes, heads or tails. Okay? If you roll a die, there are 6 outcomes, a 1, a 2, a 3, a 4, a 5, or a 6. So that's what outcomes are. Now, an event is an outcome or a group of outcomes. So in this example, the event here is a sum of 4 on 2 dice. And you can get that by rolling a 3, then a 1, a 2, then a 2, or a 1, then a 3. So there are 3 outcomes that give you the result of an event with a sum of 4. So if we were going to flip a penny and a quarter at the same time, what event or events would give 2 heads? Well, I could get heads on the penny and heads on the quarter. That's the only way to get 2 heads. And the follow-up question then says, if you're flipping a penny and a quarter at the same time, what events are going to give us 1 head and 1 tail? Well, I could get heads on the penny, tails on the quarter. That's one way to get 1 head and 1 tail. But there's another way. I could get tails on the penny and heads on the quarter. So there's 2 ways that would give 1 head and 1 tail in that example. Probability. If we're trying to figure out probability of some event, okay, we set it up as a ratio, a part to whole ratio. The number of favorable outcomes, that means the number of ways to get what I want, is always the top number. The bottom number is the total things that could happen. And to write probability, they always use this capital italics P. And then the event you're looking for goes in parentheses. So let's pretend I was rolling a die, and I was looking for the probability of a 1. Well, on a normal die, number of favorable outcomes. There's only one way to get a 1. Possible outcomes, there are 6 possible things. So the probability of rolling a 1 is 1 out of 6. So here they want us to find the probability for 1 roll of a number cube. So in letter A, probability of an odd number. Let's see, odd number. The odd numbers on a regular die are 1, 3, and 5. So there are 3 ways to get what I want. And if I'm rolling a number cube, there are 6 possibilities. So the probability is 3 out of 6. Or if you'd like to simplify, we know that's 1/2. Probability of rolling a 2. Well, there's only one way to get a 2 out of 6 possibilities. In letter C here, we want the probability of a 5 or a 6. We're not picky. So there are 2 things that I want. I want a 5 or a 6. 2 things that I want out of 6 possibilities, which we know simplifies down to 1 out of 3. Now the word problem here in number 2 talks about pennies. And let's see, 3 of them are Canadian. Suppose you pick a penny at random. They want us to find the probability of a penny that's not Canadian. Well, I know that 3 of them are Canadian and that I have 11 total. So if 3 are Canadian, 8 are not Canadian. I want not Canadian pennies. There are 8 that are not Canadian. Those are the 8 that I want out of 11 total. Okay, so that's probability. Probabilities range from 0 to 1. Well, if you think about it, if we look back here, in letter A, 1/2 is between 0 and 1. 1/6 is between 0 and 1. 1/3 is between 0 and 1. 8 out of 11 is between 0 and 1. So probabilities have to range from 0 to 1. 0 means it's impossible. It could not happen. Okay? Impossible event. For example, rolling a 7 on a normal number cube. It's impossible. Normal number cubes only go 1 through 6, so it's impossible to roll a 7 in 1 roll. Something that is 0.5, we know that's the same as 50%. Okay? Flipping a coin. When you flip a coin, flipping tails is equally likely as unlikely, or flipping heads, equally likely as unlikely. And then 1. Something that has a probability of 1, also some people say that's 100%, something that is certain to happen. Go back to rolling a die. If I wanted to roll a die it is certain, it is 100% that I will roll a number between 1 and 6. Okay? So probabilities always range from 0 to 1. Now, the complement. This isn't a complement like, hey, I like your shoes. Complement is the opposite of an event. And the example I have there, rolling an odd number on a number cube, or on a die, is the complement of rolling an even. So, the probability of some event and its complement always has to equal 1. If you think about it, in the example here, an odd number, the probability of getting an odd number is 3 out of 6, or a half. Well, its complement, rolling an even number, is also 3 out of 6, or a half. And if I add those together, I get 1 whole. Okay, so that's where probability of the event and its complement must add up to 1 or equal 1. So, in letter A, rolling a number cube, they want the probability of not a 2. Okay, we've got a normal number cube here. I don't want a 2. That means I want a 1, a 3, 4, 5, and 6. There are 5 things that I want out of 6 possibilities. And now in letter B, the complement of an impossible event. Well, let's see. Impossible means it can't happen. The complement means it has to happen. Well, if something has to happen, it is a certain event. So the complement of impossible is certain. Impossible, we know, is a 0 chance. Can't happen. Certain event must happen. So it's a 1. And like we said, complements and events have to add up to 1. Well, 0 plus 1 gets us to 1. All right. Independent events, or independent probability, are events where the outcome of one event doesn't affect the probability of the other event. And you might say, well, that doesn't make sense. Think of rolling 2 dice. Okay? You roll a dice, you get a number. The second dice, when you go to roll it, that die doesn't care what number got rolled on the first die. Okay? They don't depend on each other. They're independent of each other. I know sometimes when you're playing a board game, you might think, oh, I really need a 6, and somebody else just got a 6, so I can't. Nope. It's independent. Every time you roll the die, it is independent. There's always a 1 in 6 chance on a die of getting a certain number. Now, to figure out independent events, we have a formula. It looks a little confusing, but basically all it says is find the probability of the first event and multiply it by the probability of the second event. So, let's say you were rolling a die. First event, let's say I really wanted to roll a 3, and the second event, I really wanted to roll a 2. Well, the probability of rolling a 3, and then the probability of rolling a 2, 1/6 times 1/6 would be 1/36. That means, theoretically, 1 out of 36 times that I try this experiment, I could roll a 3 and then roll a 2. Now again, that's theoretically, doesn't mean it's actually going to happen that many times. So, in our example here, we've got 4 green socks, 5 blue socks, 7 red socks. You are randomly going to draw a sock. Now this is very important. You will replace it, and then you will select a second sock randomly. So they want to know what's the probability that the first sock is blue and that the second sock is green. So let's talk about the first sock. The first sock has to be blue. Well, there are 5 blue socks out of, how many socks are there total in the drawer? Well, there's 4, 5, and 7. So total, I have 16 socks. So the chance or probability of getting a blue sock is 5 out of 16. I picked out my sock, I looked at it, and then I replaced it. So when I replaced it, there are still 16 socks in there. Now I'm going to reach in for a green sock, and there are 4 green socks. And remember, there are still 16 because I replaced that blue sock or whatever sock I got first. And now our formula says that we must multiply. Well, I would definitely want to simplify first. That means if I conducted that experiment 64 times, in theory, 5 times, I would get a blue sock, replace it, and then get a green sock. That's independent events, or independent probability. Which takes us to dependent probability, or dependent events. Okay? That's events where the outcome of one event does affect the probability of the second event. The biggest thing to think of here is like drawing cards. If you draw a card and you don't put that card back in the pile and then you draw another card, well, what you draw second depends on what happened first. If I drew the Queen of Hearts first and didn't put it back in the deck, well, I can't draw the Queen of Hearts next because it's gone. So my second draw depends on my first. That's a dependent event. So the formula is pretty much the same. Find the probability of your first event and multiply it by your probability of your next event after the first event. And I know that seems a little confusing at first, but if we do an example here, it should make some sense. So we've got a bunch of marbles in a bag. Okay, we're going to draw the marbles randomly. So first you draw your first marble. And here's the big thing. It is not replaced. You're going to draw that first marble and you're not going to put it back in the bag. So here's what they want us to find. Find the probability that the first marble would be blue and the second one would be yellow. Okay? There are 7 blue and there are 9 yellow. So let's talk about the first draw. My first draw, I'm looking for a blue marble. Well, I see 7 blue marbles out of, let's see, this is my first draw, so there are 16 marbles in there total. Now I know I'm going to multiply. My second draw. On my second draw, let's see, I didn't replace that marble the first draw. So on my second draw, there are only 15 marbles left in the bag. On my second draw, I want to get a yellow. Well, there are 9 yellows. There were 7 blues first. I drew it. I took out that blue marble and I set it on the floor. I didn't put it back in the bag. So now when I drew the second time, there were only 15 marbles. 9 of them are yellow. And again, to multiply, I'd like to simplify first. I don't see any more simplifying we can do. This means if I conducted this experiment 80 times, 21 of the times, I would draw a blue marble first, not replace it, and then I would draw a yellow marble second. So that's independent events, or said that wrong. That's dependent events, or dependent probability, because the second draw depended on the first one, or the second draw changed because of the first one, since I didn't replace the marble. All right, good luck.